Now a function f is said to have removable discontinuity at a point x equal to a. Now carefully observe this condition. If limit extends to a plus f of x is equal to limit extends to a minus f of x, that means your left hand limit is equal to the right hand limit, but their common value is not equal to f of a. This is a case which we are discussing at the time of looking at different options of discontinuities. What happens? The left hand limit exists, right hand limit exists, they both are equal, therefore the final limit exists, but this limit value is not equal to the functional value. Let's see graphically what happens in this case and why we called it as removable discontinuity. What was the reason behind calling it as removable discontinuity? What happens is, at the point A, when I calculate the left hand limit, this is the point where I am getting the left hand limit. So this is our left hand limit. Now let's see what happens to the function from the right hand side. From the right hand side also the function is approaching the same point. So the same point also acts as the right hand limit. Therefore both of them are equal. Then we called it as the limit of the function. But this limiting value is not equal to f of a because f of a is defined at some other point. Now there is a gap in between these two, right? So graphically speaking, when I draw the graph, I move from the left hand side to this point, but I cannot continue the graph because at A the graph has come down here. There is a gap in between, and then when I continue the graph goes. So I cannot draw this graph at this point A without lifting the pen. That's why the function is discontinuous. Now see the definition. Why do we call it as removable discontinuity? If I redefine the function as originally f of a is the value at a, but if I redefine this value as f of a as at x equal to a, the function value is, that is f of x is L instead of f of a. If I remove this and define it as L, that is if this point also comes here, then will the graph become continuous there? Yes, this only depends on defining one single point, right? And such a redefining the function which makes the function continuous. That's why this kind of discontinuity is called as removable discontinuity at that point x equal to a. Is idea clear? So when do we say a function have a removable discontinuity? Of those discontinuities which arises because of the limit existing but the limit value is not equal to the functional value, such a discontinuity is called as removable discontinuity. It can be removed. Now what about the opposite case of this? A non-removable discontinuity. There is a discontinuity but it cannot be removed. When is it possible? If the limit itself does not exist, then we cannot remove such a discontinuity, and such discontinuity is called as non-removable discontinuity, or we say essential discontinuity. Now what are the different cases that gives us non-removable discontinuity? These are the cases where limit does not exist. So when does this fails? Maybe limit extends to a minus f of x may not exist. That is one-sided limit may not exist. In this case, the discontinuity becomes essential discontinuity. Or maybe limit extends to a plus f of x may not exist. That is the right hand limit may not exist. Then also the function exhibits essential discontinuity or non-removable discontinuity. There is one more case. Maybe limit extends to a plus f of x and limit extends to a minus f of x. Both exist but they are not equal. Then also the function's limit does not exist and therefore it becomes a non-removable discontinuity, right? Now the name we gave for such a kind of discontinuity is jump discontinuity, isn't it? We'll see how the graph looks like. And the name we gave for these two kind of discontinuities is infinite discontinuity. Remember, when one-sided limit does not exist, then we said it is infinite discontinuity. Whereas if both the side limits exist but they both are unequal, then we called it jump discontinuity. Now let's see this jump discontinuity and infinite discontinuity in graphical in detail.